important property. Okay, that must be considered in any practical applications of the system. Now, unstable system usually exhibit erratic and extreme behavior and cause overflow of any physical implementation. Therefore, actually, for our practical purpose, whatever system we want to design, that should be a stable system. Okay. Now, how can I define a stable system? Let us see. Suppose an arbitrary relaxed system. You have an arbitrary relaxed system. A relaxed system means initially it is relaxed. Okay. And this system is said to be stable, or another term I can use for this stable system is bounded input and bounded output system. Okay. Sometimes it is called stable, or sometimes it is called bounded in, bounded out stable system. Bounded input, bounded output stable system. Okay. So this system is called stable or bounded input, bounded output stable system if and only if the bounded input can produce the bounded output. A bounded input can produce a bounded output. So what can I write? An arbitrary system is said to be stable or bounded input, bounded output. Okay, this is also sometimes known as BU, stable. If and only if a bounded input to the system produces bounded output. Okay, so this is the definition of stable system. If a bounded output cannot produce bounded input to the system cannot produce bounded output, then it will be unstable. That means in that case, actually, a bounded you are giving bounded input to the system, but at the output you are getting unbounded output. Okay. So in that case, a bounded input is not giving the bounded output by that system. So that is unstable. Stable system is this one. Now let us try to get the idea in the form of mathematics. Suppose you have a system like this. This is a discrete time system, and here you are giving input, and you are getting output here. Okay. So sorry, this will be xn. Okay, xn, and the output is output by n. Now this input xn will be bounded if and only if the magnitude of this input is always less than equal to some finite number mx, okay, for all n. Then xn is called bounded. If this is mod xn is less than equal to mx less than infinity, okay, then the input is bounded. Input xn is.
Sir, what is mx, sir? Could you repeat what mx is, sir?
Mx is any finite number, I told you. This is less than infinity. Any finite number. Okay. That means xn should be always finite. The physical meaning of this equation inequality is that since mx is any, since I have written here ms less than infinity, that means it is indicating that this is a finite number. That's why I have not written this as explicit in language explicitly. Okay. So then the input is called bounded. Have you got this point? Similarly, if yn, this is the output magnitude of yn, mod yn is less than equal to my less than infinity, then the output yn is bounded. Okay. Clear? So here a system, this discrete time system will be stable if you apply some xn which is bounded, means which is finite and fulfilling this condition, inequality condition. And that input, that sequence is generating ক্লাস নিচ্ছি, পরে কথা বলছি। And yn will be bounded if this condition is satisfied. Suppose you are giving this an input which is satisfying this condition, this xn mod xn less than ms, and this input is generating some output yn which is satisfying the second condition. This is the first condition and this is the second condition, satisfying the second condition. Then I will say that this discrete time system is stable system. So this is a condition of stability. You are giving some bounded input at the input side of the system, and due to that input you are getting some bounded output sequence yn. But if you see that you are giving the input xn which is bounded, but at the output you are getting some yn which is not bounded, then it is unstable system. Okay, so this is the difference between stable and unstable system. Okay, now next I want to discuss about the interconnection of discrete time system. So interconnection of discrete time system. I am writing this. Okay. Suppose a system is like this. Now, if the input is xn and output is yn, then generally we write yn is equal to response to xn, or sometimes in some books you can get that output yn is written as a transformation of xn. This is response. Actually, R and T, these are nothing but transformation operators. Okay, so you can write either this or this. Whatever you will write, that is correct. Okay. Now let us write transformation for our case. Okay. These are actually replaceable, R and T. Now let us suppose we are taking transformation operation, okay, for a discrete time system. We can represent the output sequence as a transformation of input sequence. Okay. Now, two systems are cascaded if this is a serial cascading. Okay. Suppose this is system number 1, DTS1, and this is DTS2. I have two systems cascaded, and suppose the input of DTS1 is this, and you are applying some input here xn, and the output of DTS is this, it is suppose yn. y1n I am giving some suffix. Output of this DTS1 is equal to y1. And here this y1n is now behaving, is coming to the input of the DTS2. And final output, suppose this yn. This is the final output. This is the output of DTS2. Now what you can write, yn, you can write yn is equal to some transformation. Suppose I am writing here T1n, T1, action. Okay, this is yn. Yn is equal to this. And this is your transformation operator, T1, tau 1, T1. This is T2. Okay. Now then what about this? Yn is equal to transformation of, suppose T2 is the transformation, and this will be y1. Okay. So here you can write transformation of y1 is nothing but this T1 action. Clear? So you can write this equal to tau 2 tau 1 into x. Now suppose I am assigning tau c or tc. Sometimes it is called tau also. Okay. Tau c or tc. This is equal to t2 t1. Okay, this transformation operator. So what you can write, this implies that yn is equal to tc action. This is tc action. This is the overall transformation operator. Okay. Now, if you interchange the position of the two discrete time systems here, this tau 2 operator is here. Suppose you are giving here tau 2 and you are giving here tau 1. Then what will be the case? Just here, if you interchange the operation, then yn will be, if we interchange the position of the systems, then yn will be, in that case yn will be, but I am writing in that case y dash n. Okay. Okay. Then in that case, actually, it may be that this y you are not getting yn. You may get different output y dash n. So in that case, y dash n will be equal to tau 1n, tau 1, tau 2 into xn. At the input, you are giving the same signal xn, but the output may be different if you interchange the position. Okay. That means I want to say it is not always true that this tau 1, tau 2 is equal to tau 2, tau 1. It is not always true. This is not always equal to this in general. But if the system is
Sir, one question, sir. Sir, if we're interchanging the position of the system, shouldn't it be tau 2 tau 1 xn? Y dash n equal to tau 2 tau 1 xn, because we're interchanging.
Tau 2, if you change the interconnection, if you interchange the position of the system, then first you are doing tau 2 operation, so tau 2 here, then you are doing tau 1 operation.
Okay. Sorry, my bad. So got it, sir.
Okay. So in that case, the output will be different. It will be y dash 10 in general, but sometimes it may be equal. I want to say that this operation tau 2 tau 1 is not always equal to tau 1 tau 2. This tau 2 tau 1 is not always equal to tau 1 tau 2. If it is always equal, then in place of y dash 10 I will write yn, but I am not writing that. In this case, the output will be yn, but if you interchange the position of the discrete time system, in that case, actually the output will be y dash 10 for the same input sequence. And that's why I want to write that tau 1 tau 2 or t1 t2 is not equal to t2 t1 or tau 2 tau. Okay. Okay. So this will be this t1 t2 or tau 1 tau 2 is equal to tau 2 tau 1 or t2 2n, even only if these two systems are linear time invariant system. That means linearity and time invariancy. If these two properties hold good for these two systems, then in that case they will be equal. In that case, if you interchange the position of these two systems, the output will be unaffected. You will get the same output. But in general, they are not same. Have you got this point? Okay.
Yes, sir.
That means I want to say that this operator tau 1 and tau 2 or t1, t2, they are not commutative at all. They are not commutative. Okay. So this is the serial interconnection of the systems. Now we can use parallel interconnection. For example, you can use one system here, suppose TTS1, and the transformation for this system is T1, and here another system, suppose this is your TTS2, and this is T2, this is the output, and these two outputs are suppose added. Here you are getting the final output, for example, n, and here you are applying the input to this xn to these two systems. If the two systems are connected in this way, then they are parallelly connected. Okay, and you see, suppose here at the input of this system 1, you are giving the input xn, and at the input of the system 2, TTS2, you are giving same input. And here, suppose you are getting some y1n, you are getting y2n here at the output of the second system, and ultimately after adding these two things, you are getting yn, and yn is equal to y1 plus y1n plus y. That means yn is equal to tau 1 xn plus tau 2 xn. Sometimes this is written as tau 1 plus tau 2 into xn. Sometimes it is written tp into xn, where tp is equal to tau 1 plus tau 2. Okay. So in this way, you can design more complex systems. Okay, by interconnecting different discrete time systems. Now, I want to discuss more details, a special type of discrete time system that is called linear time invariant.
Sir, 1 second, sir. Sir, 1 second, sir. Could you remain on this page, sir, for 2 minutes?
Yes, yes. Hello?
Sir, could you remain on this page for 1 minute, sir? I just need to read through one thing, sir.
You want to write it?
Yes, sir. Yes, sir.
Okay, okay, you write it.
Yes, sir. Thank you, sir.
Now, next, I want to consider linear time invariant discrete time systems. Linear time invariant discrete time system. I want to analyze this. Sometimes it is called LTI systems. If the independent variable is time, then we will call this as linear time invariant system. But if the independent variable n, here suppose n is the independent variable, na? N is the independent variable. If this independent variable is space variable, then I will call it linear space invariant system. But here I am thinking that this n is a time variable, and that's why I am writing linear time invariant system. Okay. Now, input-output relationship of any linear time invariant system, actually, I know discrete time system input-output relationship of discrete time system is given in this form in general. Okay, that is a function of yn minus 1 comma yn minus 2 comma, okay, dot dot dot, suppose yn minus capital N comma xn comma xn minus 1 comma dot 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 comma xn minus capital N. Okay, it's a function of all this input, shifted inputs and shifted outputs. Okay, this is the general case. Okay, but in case of linear time invariant system, we can represent yn in this form. Yn is equal to using actually LTI system can be represented this form. Using this is minus some k is equal to 1 to capital N a k y n minus k plus summation k is equal to 0 to capital M b k x n minus k. Okay, where ak and bk are constant parameters, that specify the system, and independent of xn and yn, and independent of xn and yn. So ak and yk, they are constant terms. Okay, so this constant terms will specify the type of the system, and this ak and bk, they are independent of the input and output xn and yn. Okay, now you see this particular term capital N is called the order of the system. This capital M is not the order of the system. If I tell that what is the order of the linear time invariant system, if it is written in this form, then answer will be this N. N is the order of the system. It is not that this M is not order. This M is not the order of the system. Always try to remember that. The maximum delay, the maximum amount of delay in the output of the difference equation. This is nothing but difference equation. Okay, so the maximum amount of delay. What is the maximum value of k? K is the maximum value of k is capital N. Therefore, the maximum amount of delay at the difference equation, here it is capital N. Okay, so maximum amount of delay at the output of the system denotes the order of the system. The maximum amount of delay in the input sequence is not the, or input signal is not the order. The maximum amount of delay at the output Y. Okay, what is the maximum delay in Y? This is capital N. This is the order of the system. Okay, so here, for example, suppose Yn is equal to a_yn minus 2 plus a1 yn minus 2 plus a2 yn minus 1 plus a3xn. If I write a difference equation in this form, then obviously the order of the system is 2, because here the maximum amount of delay is 2 and it is in Y. This delay is in Y. Okay, so if you write yn is equal to a_yn minus 1 a1 yn minus 1 plus bxn plus b1 plus b2xn minus 1 plus b3xn minus 2. Sorry, suppose this is 0. Okay, this is 1. This is 1. This is 2. This is b3xn minus 3. This is one difference equation representing a linear time invariant system. Then the order is 1, not 3. It is not 3. Okay. So the general form of input-output relationship of linear time invariant system is given in that. Okay. Now I want to find out the response of the system and the system transfer function of a linear time invariant, or impulse response of the linear time invariant system. System transfer function will be discussed later after discussing jet transformation. Okay. So here, what I want to do, I want to find out the system response in terms of impulse response for a given arbitrary signal xn. Okay. Any signal, let us first try to express any signal as a weighted sum of impulse function or weighted sum of unit impulse function. You know what is the unit impulse function? Unit impulse function is already defined. Unit impulse function, it is defined as delta n. And delta n is equal to 1 for n is equal to 0 and is equal to 0 for n not is equal to 0 for other values of n. This is unit impulse function. Okay. If this is the definition of the unit impulse function, then any arbitrary signal xn can be represented as weighted summation of this impulse function, unit impulse function. So suppose xn is given, xn is equal to 1, 3, 2, 1, 1, 3. Suppose this is our sequence, a signal, and the origin is here. That means the value at n is equal to 0, the value of xn at n is equal to 0 is equal to 1. And so here 0, n is equal to 0, here n is equal to 1, here n is equal to 3, n is equal to 3, n is equal to 4, n is equal to 5. Okay. Now, you know, if you plot this, then n is equal to 1 means this sample you are getting, then n is equal to 3. Okay, 3 means here you are getting this sample. N is equal to 2 means here, suppose you are getting this sample, then again 1, then again 1, then again 3. So this is the graphical, this is N, and this vertical axis is X. So this is the graphical representation. N equal to 0, what? N equal to 1, 2, 3, 4, 5. Okay. Now, if you think about this delta n, what is delta n? Delta n is equal to this. This is your delta n. Here, n is equal to, here this is 1.0. Okay. Here this value is 1, here 3, here 2, 1, 1, and 3. Okay. But for delta n, it is always 1. And this function exists only at n is equal to 0. Otherwise, it is always 0. For other values, it is 0. So here 0, here 3. If you suppose I want to get this. I want to get this delta n minus 1 or n minus 2, suppose. Then what will be the case? And here it is 0, here also 0, here n is equal to 2. At this point, the delta function will be shifted. The value is 1. This is delta n minus 2. Okay? It is shifted to the right hand side. Similarly, if it is delta n minus 3, then the pulse will be here at this point. N is equal to 4, the pulse will be here at this point. Okay. So this is the case. Now, if this is the case, then I can represent this signal as a summation of delta C. How to see? Suppose this is the first sample. This is the first sample. So first sample is this. This sample can be represented by delta n. Then the second sample. Then the second sample. What is the value of the second sample? Just since I do not have large space, so I am writing here. This is 3. Value is 3. Okay. This is the second sample. This sample I can write that this is nothing but 3 delta n minus 1. 3 into delta n minus 1. The value of delta n minus 1 is 1, since it is shifted at n is equal to 1, and the value is 3, so I can write this. Similarly, here I am drawing in this side. Okay. Similarly, this another sample at n is equal to 2, at n is equal to 2, another sample you can get. Suppose this is, the value is 2. Value is 2. And this is n is equal to 2. This is at n is equal to 2. This is at n is equal to 1. So it will be 2 into delta n minus 2. This. Okay. Then another sample you will get here. 1 at 3. It will be delta n minus 3. Then another sample you will get here at n is equal to 4. The value is 1. N is equal to 4. This will be delta n minus 4. Value is 1. Here value is 1. So delta n minus 4, it is delta n minus 3. And finally, again at n is equal to 5, suppose another signal is there. And this is 3 delta n minus 5. Okay. Since the value is 3 and it is situated at n is equal to 5. So we are getting, this is one sample, this one. This is another 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 sample, this one. And this is another sample, this one. If you add all these sample values, then you will get this expression. If you add all these samples, you will get xn. So xn can be written as like this: delta n plus 3 delta n minus 1 plus 2 delta n minus 2 plus delta n minus 3 plus delta n minus 4 plus 3 delta n minus 5. Sorry. Delta n minus 5. Okay. That is why you want to say that whatever signal is given to us, discrete time signal is given to us, I can write that discrete time system as a weighted summation of delta functions. So here, what I want to write, for this particular case, xn, for this particular case, xn is nothing but some constant ak delta n minus k. I can write in this, where k is equal to, I am starting 0 to 5 for this case, where a0 is equal to 1, a1 is equal to 3, a2 is equal to 2, a4, a3 is equal to 1, a4 is equal to 1, a5 is equal to 3. Clear? I can write in this form. Suppose this ak is equal to xk. Now, ak is equal to xk. We see this. ak is equal to xk. What is x1? What is x0? x0 is this one. That means this is equal to a0. What is x1? x1 is equal to obviously a1. This one. Now, if ak is equal to xk, then I can replace this ak by xk. Clear? Therefore, what I want to say that this is a finite sequence and only 6 components are there, 6 elements are there, 1, 3, 2, 1, 1, 6, 3. But it may be that xn may have infinite number of sample values. Okay, so whatever may be the case, what I want to write here, so xn can be written in this form, xk delta n minus k. Clear? xk delta n minus k. Okay. You are taking summation over k. K is the root. So xk can be written in this form. The xn can be written in this form as a weighted function, weighted summation of delta functions. Okay, today I am stopping here. Next day I will discuss this part in a second. Okay, the next part. Okay, so let us stop here.
Thank you, sir.
Thank you, sir.